work, energy. Do you remember what's work?
What are we going over? Mr. Brown, what are we going over?
Work. What is work?
Change in energy.
Change in energy. F dot D. Anyone else?
Go Chintan. Participate.
F E. F V.
Yeah.
PT.
Oh, that's power.
Times it, whatever.
PT.
F V times T. Okay, I'll accept that. That's work. Good, nice recovery, Juan. Awesome. All right.
What about F delta?
All right. F delta D.
Mad.
Who's visited? What's visited?
FBT.
It forces mass times
M A D. Why?
Yeah.
Forces mass times acceleration. Wait. Sum of forces. Wait, if it's like straightforward.
You can't be adding to like that.
All right. Now,
1/2 m delta.
here we go. Work, everybody. There is a. When you think about work, first of all, we're getting into the concept of work and energy. We're going to talk exclusively about work at the beginning, and then we'll work our way back, no pun intended, into energy. Okay? It's kind of the opposite way we did that last year. Okay. We've talked about forces. Forces cause accelerations, and forces cause changes in motion. Okay? But you can also think of forces in a different way, a non-vector sort of way, as for what they do to an object. And it comes, we get this, they had many years ago, when they were discovering the foundations of physics and motion and all that sort of thing, they had this idea of momentum already, this quantity of motion, mass in motion, but it was a vector idea. Okay? And I don't remember who it was, Descartes or somebody didn't like that. And so they started to try to devise a way to analyze motion that did not involve vectors. Okay? And they came up with this idea that eventually rounded out into what we call today kinetic energy. Okay? Kinetic energy is a non-vector idea. And energy itself at first is a little bit hard to understand because it's somewhat vague. All right? Like if you look up what energy means in the dictionary or in a physics book, it generally says that energy is the ability to do work. If you look up what work generally is defined as a change in energy, which tells you absolutely nothing, right? You defined one with the other. So it's easier for us to point out things that have energy than it is for us to define exactly what energy is a lot of times. Okay? So the deal is that energy, like the definition says, it's the ability to do things. Okay? And there are different types of energy. There is energy of motion, which we call kinetic energy, which we've studied before. And then there's a whole list of potential energies, okay? Energy of motion is kinetic energy. All these potential energies, though, they all depend on a specialized location of things, all right? Like, for instance, gravitational potential energy. Where the object is located makes a difference as to how much potential energy it has. How it's located relative to the Earth, okay? Gravitational potential energy. And for a spring, spring potential energy or elastic potential energy, the energy depends on the specialized location of where the spring is located, how much it's compressed or stretched, okay? What about electric potential energy? Yeah, the location, distances of where the charges are at, right? Where they're located. You could do the same thing if you wanted to develop one for magnetic potential energy, where the magnets are located, things like that, okay? Even chemical potential energy is because of the specialized location of where the atoms are located in the chemical arrangement, okay? Some chemical arrangements and bonds, the way they're set up, have more energy than others, okay? So any type of potential energy is due to a specialized arrangement of stuff of some kind or another, okay? We're also going to learn, we've kind of learned this last year, but we're also going to learn that you can only have a potential energy or define a potential energy if you have a specialized type of force function, okay? A force function that depends on location, which is why location makes so much difference for potential energy, all right? We'll talk about that a little bit later. There is another type of energy we need to be aware of. We talked about it last year. We won't talk about it as much this year, but that's thermal energy. Thermal energy is a unique kind of energy. All the other kinds of energy are an organized form of energy. Like kinetic energy, all the atoms in this object are moving in the same direction at the same time. Okay? And if it's potential energy, they're all in a specialized location. But thermal energy is a randomized kind of energy. It's the energy of random motion and random potential energy if they have atomic bonds, like in a liquid or a solid. Okay? And so it's a little bit different. Just as a reminder from last year, remember that all other types of organized energy, kinetic and potential, will naturally degrade into potential energy, this randomized energy, but will not naturally move backwards, okay? So it's natural for kinetic energy to turn into thermal, but it's not natural for thermal to turn back into kinetic. So like for instance, you could like throw a piece of, or drop a ball, and the ball drops and bounces and eventually comes to a stop. And all of its kinetic energy, most of its kinetic energy, is turned into thermal energy. Okay? It's a natural process. But the reverse is not natural. The ball won't spontaneously cool off and begin to hop around and fly into the air. Okay? We don't see that happen. It would be a very dangerous world if that was true. Things would cool off and begin to fly around. Right? It would be really weird. That's right. So, correct. The ice caps would begin to move around but get larger. Ooh. Yeah, it is kinetic, but then that eventually, even that sound dies out and turns into thermal as well. So all these types of energy degrade into thermal naturally, but they don't come back. So eventually all types of energy will turn into thermal. Okay? In case you're not aware of that, all types of energy will eventually, given enough time, degrade into thermal energy, and everything will be at the same temperature. Okay? Yeah, like if we close the doors in this room and seal it from the outside world, all the energy in this room would eventually turn into thermal energy, and we'd all be at the same temperature.
That doesn't make sense, though. If entropy in the universe is always going up, how can it be going down?
Entropy does not necessarily mean warmer. It just means more randomized energy, which is thermal energy. But that's, like if you have a hot object and a cold object, that has more order than when you put them together and the energy shares. Actually, it turns out to be a nice uniform, same temperature, right? But that's all randomized energy, right? Yeah. Actually, eventually, many moons from now. Yeah, billions and billions of moons from now, the universe will be all the same temperature, which will actually be a very cold temperature. All the stars will have burned out. No more life. Everything dead. It's a lovely thought. Yeah, that's right. That's right. No more global warming. That's right. That's right. Eventually we'll have global cooling. Eventually. All right, but the nice thing is that is a very long time away, so I don't think we need to worry about that.
Right.
Okay, so we talked about these things. Now, I want you to think about work in another fashion as well. Since we have these different types of energy, energy can transfer from one type to another type or from one object to another object, and work is the way that you can transfer energy. Okay? Work is the transference of energy, either the addition or subtraction of energy to an object, or whatever it is. Work is the addition or subtraction of energy from something, whatever it is, by way of a force. Okay? The force will either add energy to the object or take energy away from the object. Okay? So, let's talk about that. We're going to start really simple. Work done by a constant force. So we're going to go way back. So, we got a force here, and it's moving this way, a delta x. All right? So, in our most basic form, work is F delta x. All right? Let's make it a little more complicated. What if the force is this way and you're moving this way? All right. So, not all of this force is doing work. Only this horizontal portion is doing work. The vertical portion of the force isn't doing anything. So now work is equal to F cosine theta delta x. Okay? All right. Or the way we normally write it is this. We write it F delta x cosine theta. Or, since we're calculus-y people, we can just put x there, right? We don't have to put the delta. X is a displacement. All right, what are the units on that thing? Prove it.
A Newton meter.
A Newton meter. A Newton is a kilogram meter per second squared times meter, which is a kilogram meter squared per second squared, which looks to be a joule to me. Okay? So that is a joule. So work is in units of joules. All energy is in units of joules. And we're talking about scalar math here. So we've done everything vector-wise so far up into this point. So this is a scalar concept. Okay, under what conditions will work be positive or negative or zero?
If it adds.
Okay, if it adds or subtracts energy, so let me ask you this. Is this adding energy?
Yes. It's adding kinetic energy.
It's adding kinetic energy because the force in the direction it's moving is trying to speed it up, right?
Sure.
Okay, it's trying to anyway, in theory. So, but give me a mathematical way to tell whether it's positive, negative, or zero. Not this philosophical add or subtract energy.
Dot distance.
Oh, you're going too far. Okay. Under what conditions is work positive or negative or zero? All right, work is positive if theta is between 0 and 90, right? Or less than or equal to 0, or greater than or equal to 0. And then less than 90, work equals 0 when theta equals 90. And work is negative when theta goes from 90 to 180. Okay? Correcto? All right. Well, let's give this thing a physical meaning. All right, negative work. Give me an example from real life where some force is doing negative work.
Friction.
Okay, friction. So like you're something sliding across the floor. It's moving that way, but friction is that way. The angle in between is 180, so therefore negative work is being done, and it's taking away energy. In this case, it's taking away kinetic energy, right? Okay, there we go. All right, what about net work? Okay, let's say that all right, here's a real depressing thought. Okay, you get up in the morning, you go work out, because you're very ambitious, and then because you got up early. And then you go do your homework, because you didn't do it the night before. And then you come to class, and you walk all around the building, okay, and then you go home, and you go back to bed.
Zero.
Yeah, how much net work, physics-wise, on your body?
Zero.
Zero, because you're back where you began, right? Wow.
What if it was like
So,
Yeah, that's exactly right.
but the-
Just so that I do some net work tonight, I'm going to climb to the second story of my building, or the roof, whichever is appropriate, and sleep there tonight.
We should like go to different hotels every night.
Yeah, so like if you're lifting weights, you know, you're doing positive work, negative work, positive work, negative work, positive work, negative work. You didn't do anything. That's exactly right. According to physics, you didn't do nothing. All right. So yeah, you're working out, but your workout amounts to nothing. Okay. So what if we have multiple forces? What if we've got this force 1, this force 2, this force 3, this force 4, so forth and so on? How do we know if we did work? Say we're moving this way. Okay, it's the sum of the forces. So let's go back here and make it a little more complicated. Now work is the sum of the forces times x times cosine theta. Well, this cosine theta is the angle between what and what, though?
Direction.
Okay, the net force and x, right? Net force and x. Very good. All right, so that's a little more complicated. All right, so let's take this and see. Let's move on to our next equation then. Then we'll get this work equation to be more and more general as we move along. All right, this is kind of cool. Okay, F equals ma. Right? Okay. Let's say we're just talking about one force in the x direction, and so we're going to have acceleration in the x direction. Everybody okay with that? All right? All right, because I can, and because math tells me I can do so, I'm going to do this. I'm going to multiply by delta x and delta x. All right? According to math class, that's all good, right? Okay, will you do this for me, please? V squared equals V naught squared plus 2a x minus x naught. By the way, x minus x naught is actually delta x. Will you rearrange this for a delta x, please? What does that equal?
V squared minus V naught squared over 2a.
V squared minus V naught squared all over 2.
Oh, 2, yeah.
Not all over 2a. All right, let's plug that in for this right here. So we get fx delta x equals m. I get a v squared minus v naught squared over 2. Does that look familiar?
Yes, if you were.
Let me rearrange that. 1/2 mv squared minus 1/2 m v naught squared.
Is that what you're saying? Kinetic energy. Oh, that.
Ah,
Wait.
this left side is work done in the x direction
Oh.
equals kinetic energy final minus kinetic energy initial, or delta kinetic energy.
I like that.
Isn't that kind of cool?
It's just like.
All right, so what's that?
Yes.
Wait, sorry, we did a kind of a backhanded proof here. All right, so here's the deal. What does work do? Work changes energy. In particular, work changes the kinetic energy. This is called the work energy theorem, or work kinetic energy theorem. Work changes the kinetic energy. So if work is done by any force, that force will cause a change in kinetic energy. All right? So, let's take a look at that. Board does not like to be erased. All right, so here we go. Because I like rockets.
I wonder why. Hello.
All right, let's say the mass of this thing is 500 kilograms. And let's say it starts with a velocity that equals 0, and it ends up with a velocity of something I don't know, way up here somewhere. Okay? All right, let's say that the rocket is burning rocket fuel and being very rocket-like. And since my rocket is actually red and my flames now are green,
Good work, Colin.
All right, let's say the thrust from the rocket is equal to 10,000 newtons. Okay? All right, will you please calculate? Oh, I need one more bit of information. Let's say that this thing is moving. When it goes from here to this location here, that distance, delta x, is, what do I have down here? 1,000 meters. Okay? All right, will you please calculate for me how much work does the thrust from the rocket do on the rocket? How much work does the rocket motor do? 10 million newtons.
Joules.
Meters.
10 megajoules.
There you go, I like that. 10 megajoules of work. Mega. Because work done by the rocket motor
Are you guys to go through that?
equals F x cosine theta. Do I have to worry about this cosine theta?
No.
They're in the same direction, right? Force and x are in the same direction. So I just end up with 10 megajoules. Nice. All right. So how fast will it be going?
Wait, when?
At that point.
There.
0.
Oh.
0.
No. Wait a minute, I can do this.
It's on maximum height, therefore
That's
that's
when
when
it
it goes down. Then it keeps going.
Whoa.
So wait a minute. Since work
Mr. Bruin.
equals the change in kinetic energy.
Are you saying, Mr. Bruin,
Yes.
at that point does the thrust stop, or is that when the rocket stops?
I'm just saying, when it gets there, how fast is it going? So how fast is it going?
200 meters per second.
200 meters per second. How'd you do that?
1/2 mv squared.
What's our initial kinetic energy? 0. So 10 megajoules equals 1/2. What's our mass? 500 v squared. And so you end up with a v of what?
200.
200 meters per second. That is so wrong.
Shouldn't we like?
How is it wrong?
Okay, thank you. What did we forget?
Nothing.
Is that the only force doing work?
So
No.
Wait.
Well, if it's in space, then this is correct.
That's why I was assuming.
Nice.
It's a rocket. It's a spaceship.
You're going to go into... yeah, that's right. It's a spaceship. It's not an Earth ship. I like that.
You would do labor and shit.
You're going to go into public negotiations, right?
Oh, I really would like that.
All right, so if we were in space, this is correct. Let's say we're on Earth. Trapped. All right, if we're on Earth, is that the only force doing work?
No.
What else do we have doing work?
Wait.
Wait.
Drag.
And drag.
Oh, drag. We're on our atmosphereless Earth.
Can we be on the moon?
Atmosphereless Earth. We are on
But of course, come on.
alive.
You should know that. So what force of gravity do we have? What is our force of gravity?
5,000.
5,004.
5,000. You must be using 10. I don't like that. That's
I'm
so
doing
cheap.
I'm doing multiple choice questions.
How about 4,900? Is that better? I think it is.
4,999.
See, now that I use
99. Why 99?
Just so it can be near 5,000.
All right, everyone. How much work is done by gravity?
A lot.
that times 1,000.
Okay, the work
4.9 million.
done by gravity is Fx cosine theta. So all of you that are saying 4.9 megajoules, you're not right.
Negative.
Why negative?
Because cosine theta is -1.
Okay,
Because
because
gravity is trying to.
because it's moving that way, but gravity's that way. So the
Yeah.
angle is 180. All right, now let's redo this, and let's say, look, this should be the net amount of work done.
Net.
What is our net work done on the rocket now?
Well, it's going to be
Well, that's going to be
5.1
10 megajoules minus 4.9 megajoules for a grand total of 5.1 megajoules. And so we're going to have a new velocity. Should it be more or less than 200?
Less.
It better be less. If not, we're in trouble. We're really cool. We've created some crazy new fiction. All right. What's our velocity now?
142.8.
143, it sounds to me.
The fiction force.
143 meters per second. All right, there you go. Now look, we could figure out how fast this thing's going by using the concept of work. We just got to remember that we need to use the net force or the net work, whichever you prefer to think of it as. You could figure the work for each individual piece and add them together, or you could have just done this with the net force times the distance, and you would have got the same answer. All right, well, we could also solve this another way, right?
Yes.
We could have just done F equals ma. What's our net force? Around here.
5,100.
It's 10,000 newtons minus 4,900 newtons equals 500 A. So what's our acceleration?
10-ish.
10-ish? Yeah, 10.2-ish.
I was close.
All right, and then once we have the acceleration and how far we're going, how can we find out how fast it's going?
B squared.
Yeah, we could do this. V squared equals V naught squared plus 2ax minus x naught thingy. And we'll end up with, guess what? 143.
Cool.
All right. Now, we're going to end up with the exact same thing because that's the way we derived the work kinetic energy theorem anyway, right? So we should get the same answer. All right, so there we go. Work changes the kinetic energy of an object. Work by all combined forces. All right, so wait a minute. That was too easy. What if our force is not constant? Dun, dun, dun.
I think it is constant.
Or what if it's not constant? What if our rocket is taking off and it goes from little old Earth
Because in space, so there is
and it goes from here to here? Will the force of gravity on it be constant?
No.
Oh, no.
Radius changing.
Is that
You're talking about
Integral.
and then increases as you go.
All right, everyone. The work will be done by a variable force because gravity is force of gravity.
that equation.
Yeah.
Yikes. So we have to
Integrate.
integrate. So, all right, here we go. Here's our next greatest form for the equation for work.
Oh boy.
Work now equals integral of what?
Mass.
That fun stuff.
FDX.
F dx.
Yeah.
All right, so there we go. F dx. So let's get a little practice at that.
But in DX you get
Okay.
All right, so here we go. What if we have a force in the x direction that just happens to be negative 3x squared plus 5? Will you please tell me how much work is done going from 0 to 4 meters? Work is done.
Oh, that's what I got.
Negative 44 joules. Does anybody need a calculus review of that, or are we okay? Because that is essentially just a calculus problem, right?
Yes.
The physics tells us it's a calculus problem. Once we have the equation, it's nothing more than a calculus problem. Okay? So it's just work equals F dx integral from 0 to 4. Right? 0 to 4 meters. Because we are no longer in math class. We have units, right? All right. And our answer is negative 44 joules. And done and done. Okay, now let's talk about springs just a bit, because it's time for us to progress into something that you are familiar with that has a variable force. Let's talk about springs. Our force for springs, F equals negative Kx. Okay? All right, and it looks like this. If this is our equilibrium position right here, x equals 0. And let's say that I compress this spring to here. I compress it a distance x, which is, it doesn't matter. Let's just make it a distance x. Okay, we could put numbers on it, but we don't have to. Let's just leave it like this. Say it's a distance, is that x really?
Well,
No.
negative.
Well, we have to define which way is positive, right? So why don't we define this way positive? Okay? So that would be a negative x, all right? So let's figure out the work that's done. Work equals integral from 0 to... Let's define what we want to find, okay? All right, let's define what we want to find first before we get too far, because this can get ourselves all confused. So let's do this. Let's say that I press the box, or whatever this is, this mass back to here, and then I release it. Mass, and then I release it. And let's figure out the work done by the spring. Okay? So work done by the spring is going to push it from here to here. Okay? So force from the spring dx. Right? That's our work equals integral F dx. But our force is going to be the force from the spring. Okay, what are our limits on our integration?
Negative x.
Okay, where does it begin?
Negative x.
Negative x. Negative x to 0, right? Negative x to 0. Now, which way is our force?
To the right.
Our force is to the right,
And our displacement
but our displacement
is to the right.
and our displacement is to the
Right.
right. So do we have to worry about any negatives as far as that goes for work? Because remember we have that cosine theta that we've conveniently neglected here for a minute.
No.
Okay, and they're both in the same direction. We will get back to that cosine theta in just a minute. Okay? All right, so let's put in here what our equations are. Our equations are integral negative x to 0, negative kx dx. All right? Now I hope my negative signs work out. All right, so if I integrate that, what do I get?
1/2.
Negative 1/2 kx.
Negative 1/2 kx squared from negative x to 0. So what does it turn out to be?
That's awesome.
Positive
1/2 kx squared. Now if we put numbers in there, we can figure out the work done by the spring, right?
Yes.
But that ought to look a little familiar if you remember from last year.
Yes.
That, as a side note, is spring potential energy, right?
That's cool.
All right, now we'll talk more about that a little bit later, about any force that is a function of displacement. We can derive this equation for and come up with a potential energy for it. Okay? And those are called conservative forces. Any force that's a function of displacement. All right, we can figure out, if we had numbers then, we could figure out the velocity that this thing would travel, right? Because the work would equal the change in kinetic energy, right? Do you see that the work equals change in kinetic energy is going to turn into the change in spring potential energy equals the kinetic energy, right?
Yeah.
All right, and just as a side note, here's our equation, our graph. If I was going to graph force from a spring X, what does it look like? If that's my equation, sketch it for me quick. Spring force versus X. What's this equation look like right there?
It's a line.
It's a line. Where is the y-intercept?
Zero.
Yeah. The slope is negative though, right?
So it goes down.
So it goes like this, right? So there's our graph. And what we did is we just integrated from here, negative x to 0, right? So this is the area that we found, right? And that area is the work, okay? So if we have any odd function for force, if the force function looks like this, and we want to integrate from, actually let's do it from here to here, then we would have positive and negative work areas, right? Positive work area adds energy. The negative work area takes energy away. Okay, so you could have a net work of 0 in this case if both the positive and the negatives are equal. Right?
Yes.
Okay, all of you that are trying to take a nap, wake up. Okay, because now we're starting something new. Actually, maybe new. Have you talked about dot product in math class yet?
Yes.
Excellent.
Adam. Woo.
Only in Adam. Yeah, only in super fast track kids class.
Oh, really?
What do we do?
And now us. And now us. We get to have it.
Okay. Okay, we're going to take a math segue here. You ready?
Yes.
Like the self-balancing personal vehicle.
No. A dot B. Vector A dot B. Mathematically, that is the same as A, B, cosine theta. So you can see right away that if this is F, X, cosine theta, that work really is F dot X, right? So we're getting more and more general in our work equation, okay? In fact, the absolutely most general version of the work equation looks like this. Ta-da! I added the purple dot. Okay? You're welcome. So that's where that cosine theta comes from, is F dot ds. All right, now we need to talk about dot product for a little bit. So we're just talking vector A and B. General rules for dot product. Here we go. If vector A is this way and vector B is this way, then what's A dot B?
0.
Why?
There's no parallel.
Because cosine theta is 0. Okay. This is 90 degrees. So A dot B equals 0 if A is perpendicular to B. A perpendicular to B, dot product will be 0.
Yes.
Okay, if A is parallel to B, so here's A and here's B, then the dot product A dot B equals AB.
Yes.
Because the cosine of theta, cosine of 1 will be 1. So the cosine theta goes away. All right, so physically, in work, what it means is if this is F and this is X, this portion of the force right here is F cosine theta, where that's theta. So it's the portion of the force in the direction of the force. No. The portion of the force in the direction of the displacement. Does that sound better?
Yes.
Okay. The portion of the force in the direction of the displacement that gives you work. If there's no force in the direction of the displacement, there's no work done. So the perpendicular part of the force, this part up here, that gives you no work. This is the part that gives you work. Work equals yes. Work up here equals no. Okay? The parallel part of the force gives you work. The perpendicular part of the force does not give you any work. All right? So, what if we have two random vectors, A and B? So here's vector A, and here is vector B. Okay? Actually, let's do vector B like more like this. Okay? All right. Here we go. You see that this is going to have an x component and a y component. You see that this one is going to have an x and a y component. Right? Do you see that the force, or vector A in this case, that lines up with vector B, that's going to produce a dot product? And you see that vector y, the y component of A, and the y component of B are going to produce a dot product, right?
Yes.
So do you see that A dot B is actually going to be AX BX plus AY BY? Got it? Piece of cake, right? All right? Piece of cake. So let's do this. Vector A equals 5 meters in the I direction plus 6 meters in the J direction. Vector B is going to be 2 newtons in the I direction minus 4 newtons in the J direction. All right, will you tell me what A dot B is going to be?
Negative 14? Yeah, negative 14.
Negative 14?
Yeah. Yeah.
I don't believe you.
No.
5 times 10 minus 4 is negative.
He wants the whole thing.
And minus 24.
Okay. Okay, yeah. Now. That's right. 10 minus
Got it? So it's going to be this part times this part, right?
minus.
Because, and are they in the same direction, right?
Yeah.
Because if they're in the same direction, I erased it. But these two are parallel, so I just multiply them together. So I get 10. 10 Newton meters, right? So 10 joules. And then over here, these are in opposite directions, but the negative sign's already taken care of, right? So that cosine theta is already taken care of because they're in opposite directions. I get the negative sign. So 6 times 4 is negative 24 in this case. Minus 24 joules, so a grand total of negative 14 joules. So is this taking energy away?
Yes.
And there you go. All right? Piece of cake, as they say. All right? And that's it. So don't forget your dot products. All right, let's say we have an object up here. Let's say the object has a mass, and the mass is 20 kilograms. And let's say that this length from here to here is, I don't know,
4 meters.
15 meters. It's a long incline. And let's say this angle right here, theta,
30.
say theta is 30. It looks more like a 45 to me. There you go. All right. I want to know what's the velocity at the bottom, but I want you to solve it with work.
Oh.
Like right now.
Change it. Oh, change in energy.
Yeah, like right now.
It's frictionless, right?
Oh yeah, frictionless, of course. Why wouldn't it be?
Because it's on Earth.
Oh yeah. All right, so work equals integral f dot dx. Oh, that's way too complicated, right? We don't need it this complicated. Do we have a variable force? No. What forces do we need to worry about? Because we've got an mg this way, and we have a normal force up this way. Which one do we have to worry about?
Parallel component of weight.
Okay. We have to worry about
Parallel.
this one. Why not that one?
Because it's
Because dot product, it's perpendicular to the direction it's going, it does no work.
Exactly, that's what it is.
All right? So we can just say that work equals fx cosine theta, right? Oh,
No, it makes sense.
sorry, work equals fx cosine theta. Or if you prefer, if you'd like to think of it this way, you could say it's work equals the parallel part of the force towards x, or in the x direction, right? It's the same thing, right? So however you want to worry about that.
I get why you put that now. That's not what
Now here's the deal. I'm going to let you all figure this out,
okay.
and we'll see how many of you mess it up.
That's what.
I'm going to solve it all work-like. Okay, here we go. Now, everyone pay attention. Several of you, I shouldn't have picked 45 because some of you are solving it the wrong way and getting the right answer.
That's why you should have used 30, like I told
Okay, I'm going to use 30 then. Resolve it.
Wow, 15, huh?
Solve it again with 30 because I don't think you're solving
We
it
only
right.
have 3 minutes. You should solve it in 4.
No, you're faster than that. Come on.
Is it starting from rest?
Yes.
Yeah.
That's how you feel on serving.
I got 17.
Now I got it.
Me too, bad.
Ooh, very nice. I like that. Did everybody hear this? Decreasing the angle theta should not increase the velocity of your answer. Should not.
Because like if it gets to 0, it's not going to move at all.
Right.
So if it increases, I got 12.12.
12.12.
Yes.
Yes.
Okay, here we go, everyone. Now, please watch. Please watch. Here you go. All right, here's what I'm going to do. This is mg. This is the direction I'm going. This is the angle that's given. If I'm going to use fx cosine theta, is 30 the angle I want?
No.
I want 60. So it should be fx cosine 60. What's my force causing it to move? mg x cosine 60.
Equal.
Okay? Now, everybody, quiet. Quiet. All right, x cosine 60. X, this is x, cosine 60. That's this. That's the height, right? This is h,
That makes sense.
which should make sense
MGH equals 1/2.
because you should have mgh equals 1/2 mb squared at the bottom, right? Okay, now we glossed over all this stuff in previous physics classes, but the work is done by gravity. We can think of gravity in terms of a potential energy instead if we wish. I'll talk more about that next time.
I will.